is considered one of the most extensively studied moons in the solar system, yet at the same time it remains one of the most mysterious worlds known to science. In early 2025, researchers analyzing data from the Juno spacecraft noticed an unusual phenomenon within the Jupiter system. During its 66th close flyby, the probe detected a powerful flash of reflected sunlight coming directly from the moon's surface. The source of this reflection was not ice, but Loki Patera, a massive sea of molten volcanic material roughly 200 kilometers across. Although Io has long been known as the most volcanically active body among all the worlds humanity has explored, the latest observations reveal an environment that is even more violent and unstable than previously believed. In addition to giant lakes of volcanic glass, the spacecraft recorded a separate eruption whose power is estimated at nearly 80 trillion watts. In this video, we will examine the scientific evidence for the existence of these molten glass seas, analyze the colossal energy releases detected in the southern hemisphere, and explore the new magma sponge model that may explain how Io survives the destructive pull of Jupiter's gravity. When examining the raw images from Juno's most recent flyby, the most striking feature is a bright reflective region located in the center of Loki Patera. In planetary science, this phenomenon is known as specular reflection. A similar effect can be observed on Earth when sunlight reflects off the smooth surface of calm water. This signal is extremely important because it provides direct physical evidence that the enormous 200-kilometer-wide depression is not simply a frozen volcanic crater. Its surface is still covered by a liquid material capable of behaving like a giant mirror. The leading explanation is that scientists are observing a vast lake of molten volcanic glass or obsidian. On Earth, obsidian forms when silica-rich lava cools so rapidly that crystals do not have enough time to develop. On Io, the near-total absence of an atmosphere and the extreme temperature contrast between magma and the vacuum of space create almost perfect conditions for the formation of such structures. As a result, the moon's surface has a completely different texture from the rough basaltic plains visible across other regions of Io. Io's colors also contain important clues about its geological history. The images reveal a chaotic mixture of bright yellow, orange, and deep red regions. These colors are produced by different forms of sulfur. When sulfur is heated and then rapidly cooled, it develops a reddish appearance. Over time, exposure to the extremely cold surface environment gradually returns it to its more stable yellow state. That is why scientists use the ratio of these colors as a kind of natural geological clock, helping them determine how recently volcanic activity occurred. By comparing images taken in late 2024 and early 2025, researchers were able to identify regions where the crust had recently fractured and where fresh magma had erupted onto the surface. Detailed images of Loki Patera also revealed several large islands located directly within this enormous volcanic sea. These structures appear to be gigantic fragments of solidified crust that somehow remain floating on the surface of the molten magma instead of sinking into it. Along the edges of these massive formations, the images show a distinct glowing outline. Most likely, this marks the boundary where the old cooled surface gradually breaks apart and sinks back into the deeper layers of the lake, while fresh molten lava erupts through fractures onto the surface. As a result, the lake exists in a constant state of renewal, keeping its surface remarkably smooth and seemingly young. If Loki Patera represents the stable and long-lasting side of volcanism on Io, then the events of late December 2024 revealed an entirely different face of the moon, sudden, explosive, and almost uncontrollable. On December 27th, during another close flyby, the Juno spacecraft passed over Io's southern regions and detected a thermal anomaly that immediately stood out among all other active zones. This was no ordinary local eruption or small volcanic vent. The GIRAM instrument identified a superheated region covering more than 100,000 square kilometers. To understand the scale, this area was larger than Lake Superior on Earth. However, the most astonishing aspect was not its size, but the sheer amount of energy released by the eruption. According to sensor estimates, the thermal output reached nearly 80 trillion watts. Even the combined energy production of every power plant on Earth represents only a fraction of the energy emitted by this single volcanic complex in Io's southern hemisphere. Such a level of activity barely fits within current models of planetary geology. In fact, the eruption produced roughly 6 times more energy than the total instantaneous power consumption of human civilization. For this reason, it is already being described as the most powerful volcanic event ever recorded by a space mission. The extreme temperatures even created technical problems for the spacecraft itself. JIRM's infrared camera was designed to detect incredibly faint heat signatures from orbit, but this eruption was so intense that the sensor array was effectively overwhelmed. The infrared brightness exceeded the limits the system was capable of processing normally, causing the temperature readings to move far beyond the measurable range. In the raw images, the center of the eruption appeared as a completely white, featureless region. But this was not a malfunction of the equipment. On the contrary, it was evidence that the eruption was far hotter and larger than even the mission's most conservative estimates had predicted. The heated region was so enormous and the thermal distribution so uniform that it may indicate the presence of a colossal magma reservoir directly beneath the surface of the area. This does not appear to be a collection of isolated magma channels. Instead, it seems that a large portion of Io's southern crust is effectively floating above a vast ocean of molten rock. This flyby became one of the strongest pieces of evidence, suggesting that Io's interior is far less solid and significantly more molten than earlier models assumed. The amount of material ejected during this period of activity was so immense that the moon's surface was physically reshaped. Images captured only a few months later already show noticeable changes in the local terrain and regional boundaries compared to previous observations. Fresh magma flows flooded enormous portions of the landscape, burying older volcanic formations beneath thick layers of newly deposited silicate material. It is because of this relentless resurfacing process that impact craters, so common on other moons and planets, are almost completely absent on Io. This is a world where the terrain is constantly being rewritten in real time by colossal geological forces. Io's landscape appears incredibly strange, combining gigantic mountain ranges with broad plains of molten lava. Among the most intriguing structures identified in the 2024 to 2025 data was a peak unofficially nicknamed Steeple Mountain. On most volcanic worlds, mountains form gradually through the buildup of lava flows, creating wide, gentle slopes similar to the shield volcanoes of Hawaii. But Io follows entirely different geological rules. Its mountains resemble enormous, jagged, crustal blocks that appear to have been violently forced upward from deep within the moon. Steeple Mountain rises to an altitude of approximately 10 kilometers, even taller than Mount Everest on Earth. Such structures may exist because Io's crust is composed of extremely dense silicate rocks with properties similar to Earth's mantle. Combined with weaker gravity, this allows the mountains to maintain extraordinary heights without collapsing. When looking at a full map of Io, one feature stands out above all others: the near-total absence of asteroid impact craters. Every other solid body in the solar system is covered with traces of collisions accumulated over billions of years. On Io, however, no classical impact craters have ever been confirmed. The reason is that volcanic activity here is so intense that any depressions are rapidly buried by new lava flows and erased under fresh layers of molten rock. According to rough estimates, Io's surface is resurfaced by approximately 1 centimeter of new material each year. Over spans of several million years, this is enough to completely erase all traces of its ancient geological history. In fact, Io has the youngest surface of any object in the solar system, even though the moon itself formed at the very beginning of its evolution. This gives rise to a strange phenomenon sometimes referred to by researchers as the icy fire paradox. Despite its extreme volcanic activity, most of Io's surface remains exceptionally cold. Because of the near-total absence of an atmosphere, heat is not retained, so regions far from active volcanoes can cool down to around -150 degrees Celsius. In these cold regions, sulfur dioxide ejected by volcanic eruptions settles on the surface as a bright frost or a yellowish frozen coating. On Io, There are places where a thin layer of frozen gas lies directly beside lava flows exceeding 1,200 degrees Celsius in temperature. As a result, the moon's surface becomes a chaotic mixture of zones where melting and freezing occur simultaneously. Even Io's atmosphere is unstable and constantly changing. It is composed mainly of sulfur dioxide and is so thin that its existence depends entirely on sunlight. When Jupiter casts Io into its shadow for about 2 hours during its 42-hour orbit, temperatures drop so drastically that the atmosphere literally collapses onto the surface as snow. When Io emerges again into sunlight, this frozen layer sublimates back into gas, and the atmosphere is rebuilt almost from scratch. This continuous cycle of atmospheric collapse and regeneration makes Io completely unique among all moons in the solar system. This process is also responsible for the distinctive mottled appearance of its surface, clearly visible in images from Juno. But Io's unusual nature is not only driven by volcanism. Its surface is literally deformed by the immense gravity of Jupiter. As the moon moves along its orbit, its crust continuously rises and falls by nearly 100 meters. These cyclic deformations create enormous fractures and fault systems that can extend for hundreds of kilometers. Magma rises to the surface through these fractures. As a result, Io's volcanoes often form long linear chains of active regions rather than isolated cone-shaped structures. Io is almost never in a stable state. It is a moon whose surface is constantly being reshaped by the tidal forces of its giant parent planet. For many years, the leading explanation for Io's extreme internal heat was the hypothesis of a global magma ocean. It was believed that beneath the cold, sulfurous crust lay a continuous layer of molten magma covering nearly the entire moon. However, new data from recent Juno flybys has forced scientists to revise this model. An alternative known as the magma sponge concept is now gaining increasing support. Instead of a single global ocean of lava, Io's interior is thought to consist of solid silicate rock permeated by a vast network of pores and fractures filled with liquid magma. This structure forms a complex system of interconnected channels through which heat and molten material can travel over long distances. This may explain the puzzling effect where a powerful eruption in one region coincides with increased activity hundreds of kilometers away. It appears that these regions are all fed by a shared deep magma reservoir. Such a structure effectively turns Io into a gigantic cooling system. If the moon were completely solid, tidal friction generated by Jupiter's gravity would trap so much heat inside that Io could eventually become partially molten and lose structural stability. Instead, roughly 400 active volcanoes act as pressure release valves. They continuously vent heat from the interior into space. Thermal flow studies published in 2025 have shown that these volcanic systems are extremely efficient at transporting energy from the interior to the surface. This is what allows Io to maintain a fragile balance between melting and destruction. Without constant heat release, internal pressure caused by tidal deformation would eventually exceed the strength limits of the crust. The mechanism of this heating is often oversimplified as a kind of gravitational tug-of-war. In reality, the process is far more complex and far more violent. Io is locked in orbital resonance with two other major Jovian moons, Europa and Ganymede. Because of this, its orbit remains slightly elliptical, and its distance from Jupiter continuously changes. As Io approaches the planet, Jupiter's gravity strongly deforms it, stretching the moon into an elongated oval shape. When Io moves farther away, it partially relaxes back into a more spherical form. This constant flexing generates friction inside the rocks and produces an enormous amount of heat. The process can be compared to bending a metal paperclip. If done repeatedly, the metal begins to heat up. On Io, this same mechanism operates on the scale of an entire moon. Recent models suggest that roughly 1/10 of Io's mantle is in a partially molten state. At first glance, this may seem insignificant, but in reality it represents colossal volumes of magma continuously moving through an internal sponge-like structure toward the surface. This model helps explain why some volcanoes remain active for decades, while others appear and disappear within just a few days. Magma constantly searches for new escape routes, responding to the opening of fresh fractures in the crust. The sponge-like internal structure also explains the stability of Io's giant mountains. If a continuous global ocean of liquid magma existed beneath the surface, massive silicate peaks would likely sink or tilt over time. However, the predominantly solid internal framework allows the Moon to support mountain ranges up to 10 kilometers high. It is this combination of a partially molten interior and a strong crust that makes Io the most volcanically active world in the solar system without losing its overall shape. In essence, Io behaves like a giant self-regulating system that has been trying for billions of years to release the heat generated by its own orbit. To understand the source of this activity, it is also necessary to examine the internal structure of Jupiter itself. For decades, it was believed that a solid rocky core roughly the size of Earth lay at the center of the gas giant, surrounded by layers of hydrogen and helium. However, data sent by the Juno spacecraft radically changed this view. By analyzing tiny variations in the probe's trajectory during close flybys of Jupiter, scientists were able to construct a detailed map of the planet's internal density. The results were surprising. Instead of a compact, well-defined core, researchers discovered a so-called diluted core. This means that heavy elements, rock and ice, are not concentrated only at the center, but are mixed with layers of metallic hydrogen throughout the planet's interior. This region extends to nearly half of Jupiter's radius. And this has a direct impact on Io. Such a mass distribution alters the structure of the planet's gravitational field, and therefore the strength of the tidal forces that heat the Moon. For Io, which is already influenced by the gravity of Europa and Ganymede, this complex internal structure of Jupiter adds even more instability to the tidal heating process. Studies from 2025 suggest that it is precisely this smeared-out mass distribution inside Jupiter that affects the frequency and intensity of the deformations sustaining Io's partially molten interior. In addition, the diluted core plays a crucial role in generating Jupiter's magnetic field, the strongest in the entire solar system. Because heavy elements are mixed with metallic hydrogen, the planet's internal dynamo operates in a far more chaotic way than Earth's magnetic system. Io moves directly within this extremely powerful magnetic field. When its volcanoes eject vast amounts of sulfur and oxygen into space, these particles are quickly ionized by radiation and captured by the magnetosphere of the gas giant. This creates a unique electromagnetic link between Io and Jupiter, known as the Io-Jupiter flux tube. Through this system, a continuous electric current of enormous strength flows, approximately 1 million amperes. In effect, there is a giant invisible electrical channel connecting the Moon and Jupiter's poles. When volcanic activity on Io intensifies sharply, as happened during the massive eruption in late 2024, the number of charged particles in this system also increases. As a result, Jupiter's auroras become noticeably brighter. Ultraviolet images even show a characteristic footprint of Io, a bright spot in Jupiter's atmosphere that marks exactly where this electric current enters the planet's upper layers. The existence of Jupiter's so-called diluted core may also explain the overall chaotic nature of the system. One leading hypothesis suggests that early in its formation, Jupiter experienced a collision with a massive protoplanet whose mass may have been 10 times that of Earth. This catastrophic impact likely destroyed the planet's original solid core and mixed heavy elements into the surrounding hydrogen layers. Without this collision, Jupiter's gravitational field could have been very different. This means that the tidal forces which today literally tear Io apart from within could have been significantly weaker. In fact, the Moon's current hellish state may be a direct consequence of an ancient catastrophe deep within its parent planet. Volcanism on Io affects far more than just its surface. It shapes almost the entire surrounding environment within the Jupiter system. Due to the Moon's low gravity and the absence of a dense atmosphere, volcanic gases and ash can be ejected to extreme altitudes. During powerful eruptions, such as the activity of the Pele volcano, sulfur dioxide plumes can rise to nearly 500 kilometers above the surface. This is completely unlike terrestrial ash clouds. On Io, such eruptions resemble enormous semi-transparent gas umbrellas extending directly into the vacuum of space. As the hot gas rises, it gradually cools and condenses into tiny solid particles of sulfur and sulfur dioxide. These then fall back to the surface as a strange multicolored volcanic snow. However, a significant portion of this material never returns to Io. This is where the interaction between the Moon and Jupiter's magnetosphere becomes especially extreme. Io moves within a gigantic magnetic trap. When volcanic plumes reach the upper layers of the surrounding space, intense radiation from Jupiter strips electrons from gas atoms, turning them into a stream of charged particles, ions. After this, these particles are no longer held by Io's gravity. Instead, they are captured by Jupiter's magnetic field lines and accelerated to enormous speeds. This process creates a vast torus-shaped plasma structure around the planet, the famous Io plasma torus. In essence, the Moon itself acts as a continuous source of material for this system. Data from the Juno mission indicate that Io loses roughly 1 ton of volcanic material every second. This makes the Moon the primary supplier of particles to Jupiter's magnetosphere. The plasma torus also makes the space around the planet one of the most dangerous regions in the solar system. Oxygen and sulfur ions move at such high speeds that they form powerful radiation belts capable of rapidly destroying unshielded spacecraft electronics. Any future mission near Io would require extremely robust radiation shielding. The connection between Io and Jupiter functions almost like a giant electrical generator. The Moon's motion through the plasma torus creates a current of millions of amperes flowing along magnetic field lines toward Jupiter's polar regions. In ultraviolet auroral images, a bright spot can be seen that remains consistently locked to Io's position. This is the so-called Io footprint, the location where the Moon's volcanic energy is directly deposited into Jupiter's atmosphere. Observations from 2025 showed that after especially powerful eruptions, the brightness of this footprint increases almost instantly. There is also another unusual effect associated with volcanic plumes. When an eruption becomes large enough, the dense gas cloud can partially block sunlight. This creates a localized shadow beneath the plume, where temperatures drop even further below Io's typical -150 degrees Celsius. In these regions, the atmosphere can literally freeze within minutes. Gaseous sulfur dioxide condenses into frost directly on the surface. This produces an incredibly complex system where extreme volcanic heat and instantaneous local freezing exist side by side. The entire system operates as a closed cycle. Material is ejected into space, ionized by radiation, and then contributes to the formation of Jupiter's auroras millions of kilometers away from its source. The completion of Juno's 66th orbit marked the end of an important phase in the exploration of the Jupiter system. Not long ago, the best images of Io were only grainy snapshots or archival data from the Galileo mission. But close flybys in late 2024 and early 2025 completely transformed our understanding of this world. Scientists now have detailed maps of volcanic centers, information about the composition of frozen plains, and the first direct evidence of lakes of molten volcanic glass. These datasets are not just a collection of new images. They have effectively become a fundamental geological archive that will remain the primary source of information about Io for decades. As 2026 progresses, the Juno mission is gradually approaching its end. Radiation from the plasma torus is slowly damaging the spacecraft's systems, making its operations increasingly difficult. In the near future, humanity is unlikely to send another probe directly to Io. This is not because the Moon lacks scientific interest, but because its true uniqueness has only recently been fully understood, and Io is not considered a promising candidate for the search for life. For this reason, scientists will likely continue relying on the magma sponge and diluted core models developed through the Juno mission for a long time. Ultimately, Io is a true laboratory of extreme processes. By studying this moon, we gain a deeper understanding of how distant exoplanets orbiting extremely close to their stars might behave. Io reveals a world where the primary source of energy is not sunlight, but gravity itself. It is a place where geology, physics, chemistry, and electromagnetic processes intertwine so tightly that the boundaries between them nearly disappear.